Okay, we're gonna pick up with example number 9. This is in our optimization section. It says a cylindrical aluminum soda can is to hold 12 ounces of tasty beverage. What are the dimensions of the can that will minimize the amount of aluminum used? Hint, 12 US fluid ounces equals 21.6562 cubic inches. If the dimensions of the actual can are 2.6 inch diameter and 4.75 inches tall, does the actual can have the optimal dimensions? And of course, we are going to ignore the little lip indentation right here, because obviously that is going to take away from some of our capacity. So let's go back and think about this. We have a cylinder. It's holding 12 ounces. And so that 12 ounces is equal to 21.6562 cubic inches. So 12 ounces equals 21.6562 cubic inches. So when we see cubic inches, we understand, and maybe we should already know if it's giving ounces, that this is equal to volume. Okay, so we're given a volume and we are asked to figure out the dimensions that would minimize the amount of aluminum used. So we are minimizing what formula? Well, the amount of aluminum that's used, the aluminum is the part that actually creates the can. It's like all around the outside. It doesn't fill the can. Okay, the actual soda fills the can, right? The can is hollow before they fill it up. And so what are we asked for? We're asked to minimize the surface area. So we need to minimize surface area. So surface area of a cylinder is going to be this formula right here. It is going to be, let's think about this, all the way around. So that's going to be 2 pi r h. Okay, so if you were to take a cylinder apart, you would have a rectangle and 2 circles. So this is going to be your height. This part right here actually ends up getting wrapped around the top and the bottom, right? So all the way around the top would be the circumference of the circle. So that's the 2 pi r. So if you want the surface area or the area of this piece of the flattened out soda can, it would be 2 pi r times h. Now, what else do you have? You have a top and the bottom of the cylinder. They're both circles. So you're going to have 2, and then the area of each circle is pi r squared. So you're going to have that up in the top, and you're also going to have that in the bottom. So that's where your surface area formula comes from for the cylinder. We are trying to minimize this. So this is what we're going to take the derivative of and set equal to 0. But right now, your derivative has, well, your function has 2 unknowns. We have r and we have h. So we need to get this down to 1 unknown so that we can solve and figure out what our maximum or our minimum in this case is going to be. Okay, so that takes us back to volume. They give us some information about the volume. They tell us that it's 21.6562 cubic inches. You can't use the 12 ounces in this problem because our dimensions for our surface area are also in inches. Like we're assuming length and stuff like that for these. So ounces is liquid measure. We can't like mix and match our units of measure. So that's why they gave us this information right here. What we would also need is the volume formula for a cylinder. So volume of a cylinder is pi r squared h. It would be the area of the base and then multiplied by the height. So it's like if you were to take the bases and stack them on top of each other, infinitely close, higher and higher and higher, then you would get a solid cylinder. Okay, that's where this comes from. Alrighty, so I know that that is going to be equal to 21.6562. Okay, so what we're going to do is this is going to be our helper equation, and we are going to solve this for a variable. I think I will solve this for, let's see, what would this be easiest to solve for? We can solve for, how about h? Okay, we'll solve this for h. So divide by pi r squared on both sides. This goes away. And now wherever you see an h up in the top, you are going to plug in 21.6562 over pi r squared. So surface area is 2 pi r times 21.6562 over pi r squared plus 2 pi r squared. We can do some canceling. This pi and this pi can go. If you cancel this r, you're left with an r down in the bottom like that. So this becomes 2, let's see, 2 times 21.6562. I'm going to rewrite this r to the -1 like that. So it's a little bit easier to take the derivative, plus 2 pi r squared. Okay, now we haven't actually taken the derivative. That's our next step. So surface area is going to be, bring this out, -2 times 21.6562 times r to the -2 plus 4 pi r. Okay. All right. Now, let's see. Let's put this into the denominator. So like that. And then if we get a common denominator between these two fractions, I would have to put r squared under here, which would mean I would need to multiply this by r squared, which would make that r to the 3rd. Okay, now I have a common denominator, and we're going to set this equal to 0. So when we have a fraction, remember, the only thing that we need to be concerned about with a fraction being set equal to 0 is when the numerator is set equal to 0. So we're going to set that numerator equal to 0, and I'm going to use Desmos to help me out with this, especially since we have the decimals. That would make it a little bit easier. So we have, I'm going to type it just like we have it, -2 times 21.6562. And then that will be plus 4 pi, I'm going to use x instead of r squared. Okay, so there is your function. Okay, you can put y equals in the front if you want to, you don't have to. And so we have solutions here and here. Now, since this is a real life problem, we're going to eliminate the negative solution because we would not want a negative radius. R stands for radius, so we don't want negative dimensions here. So we get r equal to 1.857, okay? And if the radius is 1.857, I can find the height by plugging in what we have for r. Okay. And what do we get for that? Let's see, 21.6562 divided by pi times 1.857, like that. and we get a height of 3.712. This is inches. I want to make sure I remember my label. This is also inches. So in order to use the least amount of aluminum, our dimensions should be a radius of 1.857 and a height of 3.712. So if the dimensions of the actual can are 2.6 in diameter and 4.75 inches tall, does the actual can have the optimal dimensions? So be careful what we were given for this to compare. This is saying a 2.6 inch diameter. So we have a radius here. This is our diameter. So if the diameter is 2.6, then that means the radius must be half of that. So 1.3 inches. Okay. So it's not using the optimal dimensions, but of course, marketing and engineering and human consumption all affect the mathematics of this. So 1.3 inches is smaller than 1.857. Remember, this is a soda can. We want to be able to comfortably hold that can, right? And so probably they've done a bunch of experiments and results and had, test subjects decide like, what's the most comfortable thing to hold, like something this wide, something this wide. And so you have to take that into account. Maybe something with a 1.857 inch radius is going to be too wide to hold. And so that's why they maybe made it smaller. Who knows? Could be anything. Could be something with this lip, like they had to modify the radius so that the lip is able to be formed and not use too much aluminum. There's lots of things in play for this design, but that is how you would find the dimensions in order to use the least amount of aluminum for the can. Okay, for example number 10, we have the manager of an 80-unit apartment complex is trying to decide what rent to charge. Experience has shown that at a rent of $200, all of the units will be full. On the average, one additional unit will remain vacant for each $20 increase in rent. Find the rent to charge so as to maximize revenue, maximize the amount of money that the manager is bringing in. So let's think about this and see how this is working out. He's got 80 units, he's got 80 apartments, and if he charges $200, they'll all be full. Everybody will rent an apartment. So that would be a revenue of 80 times 200, okay? Which would be $16,000, okay? But I don't know if that's the maximum revenue, okay? So he could charge $20 more for rent, but then he would lose one apartment, like one of them would be empty. They wouldn't all be full if he charged $220. So that revenue would be $220, but then we'd lose one, so it'd only be 79 apartments that are full. And so for that, let's see if we have I still have my Desmos up here. So 79 times 220, that's going to be, well, that's a little bit more money, 17,380. So if he charges $20 more, the 79 people that do continue to rent are going to make him 17,380. Well, what's going to happen here? When are we going to actually max out and make the most amount of money? Because we could charge a whole lot of rent, but if you only have, maybe if we get down to like half our people renting, will we still be making a lot of money? Because if you don't have all of your apartments full, that's less people paying rent. So eventually this is going to max out. So we'll do it one more time. If I raise it to 240, then I'll only have 78 people renting. So 78 times 240, 18,000. So it's still making more money. And then if we continue this cycle, will it continue to make us more and more money? Well, eventually these are going to go all the way down to 0 people being able to afford the apartment. So if you have 0 people renting from you, it doesn't matter how much you charge a month, you're not making any money. So somewhere this is going to max out. What's the pattern that we see? Well, we're starting out with 80 units to work with, so that's an important number. And we're also starting out with $200. That's an important number. We know that if he charges $200, all the apartments will be rented. What happens is every time we increase the rent, this number goes up, but this number goes down. And so we have to think about like by how much and how to write that as a function. So your function is going to be R equals for revenue. And we have to let our variable, let's say let X be, let's see, the easiest way to say this would be the number of times he increases the rent. Okay, so let's let X be the number of times he increases the rent. So the first time he increases the rent, X is going to be 1. The second time he increases the rent, X will be 2, and so forth. And if we can figure out when that maximum profit occurs, then we can figure out how much rent he can charge. Okay. Okay, so let me move Desmos over just a little bit here. So how are we going to do this? Well, we know 80 and 200 have to come into play here. So if I increase the rent the first time, X will be 1. The rent will also be 220. So it's going to be $200. That's going to be part of our revenue function plus, let's see, $20 times X. So if X is 1, that would be the first time he increases the rent. If you put a 1 in here, 1 times 20 is 20. 20 plus 200 is 220. So that means that he's charging $220, which is exactly what happens the first time he increases the rent. Well, now we need to do the other part over here, which talks about the number of apartments we have. So we start out with 80 apartments. If he increases the rent the first time, when X is 1, what happens to the number of apartments that he has rented? It goes down, right? Keeps going down. How much does it go down by? It goes down by 1. And so in that regard, it's going to be going down by X. You don't just want to put a 1 there every time because then it would just be a 79. Like this would just be 80 minus 1. We want it to be 80 minus X. So like the second time he raises the rent, it'll be 80 minus 2, and then that would bump us down to 78. The third time he raises the rent, this would be 80 minus 3, which would be down to 77 apartments. The fourth time, the fifth time, and so forth. So that's why we want this to be 80 minus X. So this set of parentheses represents the number of apartments that he's renting. This set of parentheses represents how much the rent actually is. So if you put a 1 in here and here, you end up with 79 times 220. If you put a 2 in here and here, you end up with 78 times 240. Now, this we can graph, or even better, we can use calculus and take the derivative and find a maximum, okay? So that's what I'm gonna do. First, I'm gonna multiply this out. Actually, you know what? I'm not gonna multiply this out. I think We will use product rule for this. So we're going to take the derivative, dr dx. We haven't used product rule in a while, so might as well practice it a little bit. Remember, this is u and this is v. So we're going to do u prime, which is -1, times v, 200 plus 20x, plus v prime, which is 20, times u, which is 80 minus x, like that. Simplify as much as possible. I'm going to move things over a little bit. Set it equal to 0. So -200 minus 20x plus 1600 minus 20x. Let's double check that and make sure that we're all good. Negative, negative, this is positive, and negative. Okay, so combine like terms. I see, what do we got here? 1400, -20, -20 minus 40x, like that. And then if we add 40x, like this, and then divide by 40 on both sides, that's a 1400 right there. X equals, let's type that in. Oops. My Desmos screen doesn't want to like cooperate with me right now. There we go, that's better. $35. Okay, so the maximum number of times that he can, the most number of times I should say, that he can raise the rent and make the most money is going to be happening when X is 35. So what would that mean? So that would mean your revenue, go back to the original, is going to be 80 minus 35 times 200 plus 20 times 35. This represents the rent. This represents the number of units that are full. Okay. Oh, can't see that, can you? There you go. So 80 minus 35, going back to this original revenue equation, times 200 plus 20 times 35. Okay, so 80 minus 35 is 45. Only 45 units are going to be full. And then 200 plus 20 times 35. 20 times 35 is going to be 700. 700 plus 200 is 900. So if he charges $900, he will have 45 units, which is going to give you a maximum revenue of, let's see, what is 45 times 900? $40,000, $40,500. Okay, per month, by the way. That is per month. Pretty sweet.